Hello, I'm Sam, and today in this, I wanted to make a review video for equilibrium in AP Chemistry. I wanted to make this video for someone, um, you know who you are. But anyway, let's just get into it. The equilibrium in general seems like, and a lot of people agree that it's probably the hardest topic. Like a lot of my friends at school said they didn't understand anything. But it's actually a pretty simple topic, and hopefully I can explain it in a way that makes sense and like just a comprehensive view. I'll try to be as quick as possible, but I don't know. Hopefully it won't take that long. Also, I'm planning to do like a part two where I do like practice MCQ and then a couple FRQs on equilibrium. But let's just get into what equilibrium is. So, we're talking about obviously like chemicals and like reactions and stuff, right? So there are some reactions that go back and forth. Like if we had like a beaker, and inside the beaker there was like two molecules, right? These molecules are always like interacting like back and forth and back and forth. Um, And if you remember from biology, equilibrium's pretty much saying that there's a balance, like, homeostasis. And what nature wants to do is it wants to attain homeostasis within the beaker. And how it does that is that it takes like different molecules and it continues to react and react until there's a balance in the amount of one reaction of like there's a balance in the amount of product and there's like a balance in the amount of reactant, because like in a chemical equation, like this would be the product here, and then this is the reactant, right? So what does that look like? Well, this graph kind of like explains it like pretty well. So we have a chemical process over here, and I mean it's just a practice question, but estimate the value of equilibrium constant Kc. And we'll talk about Kc really quick below in this there's a graph. So let's say we have O2, NO2, and NO in a beaker. Oh, well, actually, maybe not a, well, yeah, a beaker. They're all gases though, so they're not going to be liquids. Um, what happens is that within the beaker, these products are going to be constantly like combining to form NO2. But at the same time, this NO2 is also constantly like um, going back into these reactants within the beaker. Yeah, it has to be closed. But so what happens is that you start with the same concentration of products of these two, and obviously you're not going to have any NO uh, because that's what you're starting with here. Well, no, sorry, not NO. You're not gonna have any NO2 because that's what you're starting because that's what you're trying to make like that the entire like thing here process here is like trying to make NO2. So left to its own, like in nature, these um these two will slowly like decrease in amount, but they don't completely go to like zero. Like it it levels off here, and it levels off at around like right here, or maybe not there, but like right here. Well, maybe like right here. I don't know, it's kind of hard to tell. Like here, the pixels are starting to, I don't know, somewhere around here, somewhere in that general area. Um, and this, once it levels off, is equilibrium. This is what equilibrium is. And one guy, I think John Green's brother, I forgot his name, he explained it really well, and he said that most chemists make their living by throwing off equilibrium. Like, because if you're trying to make NO2 here, you're trying to like maximize the amount of NO2 you make, and you don't want this equilibrium thing happening because you could what you could do is that all of this products could go to zero and all of this could go to like the max, like one mole concentration. And if you're trying to like make NO2, you want to maximize the amount that you make. So this is what equilibrium is, and this is what we're talking about. And we're essentially using math to study um, how these numbers are interacting with each other, how these moles concentration interacts with each other. So let's talk about a couple of things. So EQ essentially is telling us like this ratio. It's the ratio of products over reactants. Okay, so what does this ratio mean? So there's a really important expression that you need to know. I mean, it's everyone's seen this, and you're not dumb. You've seen this before. It goes like K EQ is equal to like the products over the reactants, and these exponents here are essentially the moles. I did capital letters, but it's fine. Don't worry. So uh, we have a really nice process here called the Haber process, which explains a lot of this unit. And let's you can write this expression for any like back and forth equilibrium process like this, like oops, back and forth meaning like if you have this, right? That's equilibrium. So let's just write it. So for the Haber process, we take products over reactants. Okay. So what we're going to do is that this is a product here. Well, yeah. So this is the product, and we notice that it has a coefficient of 2. So since we're doing products of reactants, we use square brackets because it's a gas, and then well, no. We use square brackets because we're talking about KS. We're talking about KEQ. We use square brackets because we're talking about KEQ. So don't worry. We'll get to the rounded brackets in a bit. So we write NH3 like this, and because it has a coefficient of 2, we're going to put that as a squared here and all over the reactants. So we see the 3 here, so we know this is going to be cubed, but there's no coefficient here, so we can just leave that alone. So this is going to look like at H2 cubed and then N2 to the power of 1, which is just pretty much nothing. And this is equal to our KEQ. Pretty cool. Like, the thing is, though, give me a second. Yes, okay, just wanted to make sure, but yes, you can write this for gases. Okay, just want to make sure, because I don't want to teach you anything wrong. So, this is the KQ. So, how do we use this? Well, like, what do we really use this for? But before that, I'm just gonna might as well show you the gas part of it. Okay, so concentration versus pressure. Okay, I'm gonna get some new space. Okay, uh, maybe down over here. So concentration, we're usually talking about molarity, right? So if you're given like a beaker of water, like how much moles per liter is in like how much like substance is dissolved in the water, that's like concentration, right? But if we're talking about like gas, like you're gonna have like a closed beaker, and there's gonna be gas particles in there. This is like the concentration version of for gas. It's called like pressure. Um, and for pressure, we have like a completely different like process for it. So we have our KEQ, right? But this is actually going to be KP, and obviously P is for pressure. So it's gonna look like rounded brackets with a big P, and then you're gonna have like your whatever equation. So if we had like the Haber process here, and we take this, I'm just gonna copy this and then just move it down there. Oops. Copy. All right. paste. All right, so if we had our Haber process, this would look like P, and then like it kind of looks like a subscript NH, whoops, NH3, and we put this here, and this becomes a 2. And then it's pretty much the same thing, except we H2 and then 3, and then you get the idea. You have to finish it out, but this is what it looks like. And on the AP exam, if we're using KP, you have to use the rounded brackets, otherwise you're not going to get the point. Our teacher told us that. Sorry, I lost my voice a couple days ago. But yeah, so how is this functionally useful? So how we were talking about how this was a ratio, right? So this kind of brings up this idea here, where what I'm talking about over here. So when we're talking about like products over reactants, we kind of like get an idea of whatever K is, like whatever given value we get for our K EQ, it tells us like what the reaction is really favoring. And we have like large and small values. And this is really relative. Whether something is large or small is really dependent on what you're comparing it to, because every single equation, like the Haber process is one, but there are obviously many others. Their K equilibrium values, their K constants, are truly like relative to each other, and like scientists like use like experimentally find like these true like KQ values, like but usually for the test they'll give it to us for us. But whether we can use these KQ values to compare it to determine whether the reaction is going to tend to favor the reactants or the products. All right, so what does favor mean? Favor means that how scientists want to make more NO2, like we were in this example, they wanted to make more NO2. There are certain changes we can make to the environment, like within the beaker or whatnot, to maximize the amount of product or reactant we want to make. And we can use the how big or small the KQ value is to like find out if what we're doing is actually going to increase the amount of product or reactant we're making. So, oh man, that sounds complicated, but if you're in calculus, you're probably familiar with like, seeing infinity over one or one over infinity. And if this was a limit, we'd say that this tends to infinity. This tends to infinity because obviously infinity, anything over one is that. So this is like infinity, but this tends to zero. So the reason I show you this is because it's a very big number on the bottom here over like a regular number. So a very big number on the bottom, if this is a very big number here, right, that means the products is being favored. The products here is being favored because there's more of it. There's simply more on the bottom, and this, because there's more here, is going to be in the denominator, and because it looks like this, KQ results in being a very small number. Okay, like comparatively. Okay, and then the same for a larger number, obviously. So we can manipulate equations. We can manipulate the K values. So what does that mean? Well, if we were like trying to find like if we were like doing, okay, whatever, I don't even know the application of this, but you need to know this for the test. Okay, so we have an example here, and let's say we have the K value for this specific thing, and if you wanted to write out the you know the this for it, you can, but we don't need to because they've just we just want to find the k value for if opposite. So what opposite means, like usually the reaction goes this way, right? But what if we wanted to find the k value for if the reaction was going this way from our product to our reactant? Just realizing I messed up my wording here earlier, but you get the so get it's fine. Okay, so all we have to do is take the reciprocal. So this k value is for this. This k value is for it goes this way. All we have to do if you want to go opposite is we take the reciprocal. So all it will be is it'll be 1 over 4.0 times 10 to the 24th. And that's super easy. That's cool. Okay, what if we, for some reason, wanted to multiply the entire thing by 1/2? So what does this mean? Like, see this 2 becomes 1. This 2 becomes 1/2. This becomes 1. So what if we wanted to do that? Well, all we have to do really is take this k value, which they already given to us, and we square it by what we're multiplying it by. So if we are multiplying it by 3, then we put a 3 here. And then we have to like obviously use our calculator to solve it. So, or you don't, maybe the numbers might be easy enough to solve without a calculator. So here in this case, it's 1/2. And if you have experience with math, obviously, this is a square root. So square root of 4 is 2, and might as well put sig figs. And then exponent rules. Whenever you exponent something that's already exponented, you take 10 to the 12. You just multiply. So this is our new KEQ when we multiply by 1/2. What if we are adding two different two separate different balanced equations? So we were originally messing with this with the SO3 and the SO2. And now let's add the second guy. And this guy has his own KEQ value. And now the test wants us to solve for what's the KEQ value of this monstrosity. And we can use what we have here and here to find out what this is. So if we notice here, this NO2 is on the left side, but NO2 was like on this side. So what we have to do is that we have to actually switch this up, like switch up these units. So what's the K value when we switch up the units? We talked about it here when we wanted the opposite. We just find the reciprocal. So what's the reciprocal of this? Well, what's 1 over 0.064? And if you put that in your calculator, this actually nicely equals to 16, which is fairly large, but we'll just go with it. So now what we have is that we can add these together. But what happens when you add them, like when you stack them on top? Because now, like theoretically, these are switched. And what you do is that you multiply these. Whenever we're adding them together like this, we multiply the k values, which is kind of counterintuitive, but it just works. So we take this this k value, original one, and we just take this and multiply it by 16. All right, and we get some value. But here's the problem, right? If you notice, all of these is like by 2. And we had like no coefficients here. So like what do we do? Well, we talked about this actually no, wait, no, we did. So all you have to do really is since it's all multiplied by 2, we take the k value and we also divide by 2. And that just removes all the extra coefficients that we have here by 2. So if you solve this, you'll get some value, and this value I did on my calculator earlier is 8.0 times 10 to the 12, not negative 12. And this will be the k value for this. Okay, so obviously there's some practice needing to be done there, but that's essentially what you do. All right, video is getting kind of long. Sorry, but hopefully you're understanding stuff. Earlier, I was talking about how we can affect our environment to do, do stuff to like chemicals. Well, do stuff to the K value specifically to manipulate this. Well, not manipulate, but we can study how things are changing. So there's a couple different things that affects it. There's concentration, pressure, temperature, and like dilution. So these four things is pretty simple. And this is all comes under something called Le Chatelier's principle. French, pretty I know. Chat. Anyway, it's Le Chatelier's principle essentially tells us that there will be like in equilibrium, there'll be something that wants to turn this equation toward equilibrium, and it depends on like that like different things can affect it, like temperature, concentration, like over here. But it says that nature always wants to restore that balance, and Le Chatelier essentially like shows you how this balance is being attained. You should probably look up a proper definition for that, but you understand stuff when you put it in your own terms. Um, so yeah, just Google search that. All right. Anyway, first thing that affects these molecules is concentration. So we have like Haber process here, right? If I added, let's say, a lot of this, right? So then it would be thrown off balance. If we had like say a scale like this, right? And then this was the products and this was the reactants. If I added a bunch of products over here, then this would like be weighing heavier than the reactants. And nature wants to balance this out by like swinging it back until it's back to the regular state. So considering that, if we added a bunch of three H's here, well, H2, a lot of two NHs will be made as a consequence by Le Chatelier. All right, that's pretty much how it works. And obviously, vice versa, if I added a lot of this, then a lot of reactants would be quote unquote made. Um, so that is what's happening there. And it's pretty simple. Um, more A, it results in more B. Huh, couldn't have put it in better terms myself. Except I did. All right, pressure. This one's can be a bit complicated, but the way I like to think about it is that obviously we're talking about gas, and when I have a couple molecules, um, all of them are free floating. So if I just take this thing here, and if I just copy this, I'm gonna bring it closer to where I am at. Oh, whoops. All right. Really useful tool. All right, so here, if we have these like H2 and then N2 in a jar, they'll be free floating. But when I put them under pressure, if I squeeze them together, they will want to tend to the together state. Um, and technically, like if you increase the pressure, they will shift to the right. And whenever someone says shift to the right or shift to the left, they're just talking about what the reaction is favoring. Um, like whenever you do something, like whenever you change the concentration, whenever you change the temperature, like it's whatever is shifting to the right or shifting to the left is favoring the products are reacted. So obviously, when we shift to the right, we're favoring the 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 product. We're favoring this because we're making that. So, and then obviously when if I were to lift this back up, it would go back to low pressure, and then everything will want to come back there. Because here's the thing that I forgot to mention earlier. The process never stops once it comes to equilibrium. Like these molecules are like whatever's in the jar is constantly like being like repeatedly like banged together. Like all the gas molecules are constantly slapping each other and turning into Na2 and turning back into NO. The process never stops. And because it never stops, it's like a refresh. It's like someone sitting there constantly hitting the refresh button, and it's constantly like refreshing from here to here and then back to here. So um, by changing like the pressure, we can like directly affect that, which is really cool. So there's also like non-rigid containers, like say a balloon. So whenever we measure pressure, we have something called atmosphere, and this is just ATM. So what this is that like say like consider like regular air in the atmosphere. That's some pressure, okay? If we say that something has three atmosphere, it means that that gas has three times the pressure as regular air in our atmosphere. So and if you remember gas laws, partial pressure is pretty much like the summation of all these different gases to the total. So in here the Haber's process, we have H2 and N2. So let's say we had a balloon, like a balloon, okay? And within the balloon, we have like one ATM of H2 and one ATM of N2, all right? That means that the total ATM is going to be 2, and that's just simple math. Like, um, what happens in a balloon is that if you added like a third unknown gas, um, okay, so then obviously the total ATM now is is 3 because all of that is in the balloon. But the thing is, the wait, no, actually, um, hold on. The total pressure within the balloon stays the same because the volume is changing. All right, this is really complicated to explain, but essentially, if you want to keep 2 ATM, okay, if you wanted to keep a total pressure of 2 ATM, and we added another ATM of like some third gas, what happens is that the balloon expands to become bigger, okay? What this does is that this gives more space for molecules like H2 and N2 to run around. But with this increased amount of space, there's also this third thing that's we didn't consider before also running around. So essentially, when we take it at face value, um, instead of having one ATM of H2 now, we have a smaller ATM for H2. This would be one third of what it originally was. So pretty much, um, one third times one is like one third. So now after the addition of this, the ATM of H2 would be one third ATM. But the total is still 2. Well, actually, no, 2 would be 2/3 ATM. Sorry, my bad. 2/3 ATM. The total is still 2 because if you took 2/3 plus 2/3 plus 2/3, it would still add up to be 2 because we added like a third gas. It's essentially what it is. If we kept it in a rigid container, which means not a balloon, uh, like if we had like a rigid container, um, and we added like obviously our H2, our N, wow, what would happen is that all of these gases within this, and we added our mystery, oops, and we added our mystery gas too, this would actually increase the total ATM from 2 to 3 because there's more pressure. So if there's one ATM of that and one ATM of that, and we added one ATM of the mystery, the volume staying the same, so there's less space for the gas particles to move around, increasing the pressure. And when we increase pressure, obviously, you know what happens. It starts to favor the products. Video is getting extremely long, but hopefully I'm making some sense. It's not easy to teach. All right, temperature. So here we have like energy. Energy is coming out of this. So usually, what the test will do is that they'll give you um, a change in G value. Like for example, they'll give you where is it? Oh yeah, they'll give you a change in H. Okay, they'll give you this H value. All right. So if this value is negative, if the value is negative value, uh, like well kj per mole or something. Okay, that means it's exothermic. Okay, and exothermic means it releases energy, so the energy is going to be on this side. If it's a positive value, then it's endothermic and the energy is going to be on this side. But that's just some basics we need to know for where the energy goes, because it's important to know that whenever we heat up something, okay, so let's say we have this process right here, okay? What happens if we add energy? Is it going to tend to the right or is it going to tend to the left? It's going to tend to the left because we're adding energy to the process and we're essentially feeding this side of it. And just like the scale we were talking earlier over here, whenever we tip the scale in favor here, it's gonna look like this because we're adding energy here. We're tipping the scale downwards, and it's going to start favoring the reactants, and it's going to start making more A and B, and that's temperature. There's another thing to temperature, but I'll get to that after dilution. Dilation talks with aqueous substances. So if we add water to shift to the side with more species, it evaporates. So essentially, we have an equation here. If we add water to this, what would happen? It shifts to the left because there's more aqueous species there. There's literally 1, 2 moles here, and there's 1 moles here. So it's because there's more like species of aqueous like solutions on this side, it's going to make more like C. It's going to make more C species, and that's pretty simple on that front. So we were talking about temperature, and what happens with temperature is that unlike dilution or pressure or concentration, there is a permanent change that happens that changes the EQ. This is because whenever we are like tipping that scale in the balance, that's actually like affecting the KEQ. Um, so whenever you're changing the temperature, you just have to know that you're also like affecting the actual value of KEQ. So that's cool. Now, earlier I was talking about how we can compare to find out whether we're making the products or reactants. Like over here, I was talking about it. So essentially, we use something called a reaction quotient to find this. And my teacher calls it like fake K, um, because it's essentially the same equation as this. However, we at different times during the reaction, like if this is like t is equal to 0 and so like t is equal to like 1 hour or whatnot, within that time span, there'll be the actual concentration, like the numerical value of the concentration will be different. And we can take the concentration at different times and you can compare to figure out if it's favoring the right or the left. So whenever a problem gives you concentrations, it'll just and it'll just straight up ask you, and you just plug it into like the KQ thing. It'll look like something, whatever. You compare these two, like they'll give you two sets of molarities, and you can compare it. And whatever whether the Q is going to be less than or greater than or equal to, shows you where the reaction is going to go. So let's say our KEQ value, okay, is less than our Q value, what happened is that it's going to favor the right side, which means it's going to make more products, sorry. It's going to favor the right side, make more products. The opposite is true for a greater than. So if the KEQ is greater than the actual Q value, then it's going to favor the left and the reactants. The way I remember this is like the crocodile method. So it's going to eat whatever's greater, right? It's going to eat that whatever's greater. So if it's less than, then it favors the right, so on. And then obviously if it's equal to, then it's in equilibrium, and nothing is really going to change from that front, although the reactions themselves doesn't stop. I can do an example of this in the next video, but I'm just trying to wrap it up. There's one last thing we need to know, and that's just the solid solubility product. So, solubility product, you're essentially like finding out how soluble something is, right? If you dissolve salt in water, there's a measurement to how soluble that salt is within water. And then like the technical definition is like 1 gram in 100 milliliters of water. So how do we find this solubility? Well, first of all, we have our own K like term thingy, and it's called Ksp Solubility Product. So usually in a question they'll give you like this, and you have to figure this part out on your own. But hopefully you can figure out how to. You just look at the periodic table to find the charges, and then obviously you can figure out if it's like aqueous. Hopefully they'll give it to you though. But this is essentially just making the equation, and that's like the hard part. After that, it's really easy because it's the same rules as before to make this, except there's no denominator. We don't need a denominator. It's just this. So how would we solve something like that? So let's say we're given the Ksp values, okay, and we want to find the actual concentration of each. Let's say like over here, the K value was like 0.64. It could be something like that. I don't know. Like it could be something like that. We plug in that Ksp here, and the thing is, something really interesting is that so obviously we're trying to like find for x. Like so, this Kca becomes x, and this F2 becomes 2x squared. This 2 here is represented twice. Like it's literally like coming up 2 times. So that's something to be careful of. And then, so this becomes 4x cubed. So then you can solve this is equal to 4x cubed. And then you get your x value. And once you get your x value, you can find Ca and F2 by like multiplying. So Ca is straight x, so that's fine. F is actually 2x, so F is going to be 2x. So you take this value of x which you found and multiply it by 2 to find the concentration of F. Whew, crazy, right? And something, just rule of thumb is that if there's a higher temperature or something, it's like 99% chance that it has a higher solubility. Well, 100% chance since we're taking the AP test, so yeah, it's just more energy to tear apart those bonds. Okay, last thing, and that's the entire unit. The common ion effect. So this is essentially what we were talking about earlier, like with their Ksp, really cool, it's awesome. And so let's just find the concentration. Why not? Let's just do some practice. This isn't common ion, but let's just do some practice of this. So, fortunately for us, well, we don't really have this. Fortunately for us, everything is already, like the equation itself is already written, so we don't really need to figure it out. Now we just have to find x. So I don't see any squared things going on here. So it's just going to be x times x is equal to our Ksp, which is just 1.6 times 10 to the negative 10. This is just going to be x squared equal to this. So all we need to do is take the square root of this. What's the square root? I use my calculator. This is just going to be 1.3 times 10 to the negative 5. And this is going to be in moles. Well, actually, it's going to be in molarity because this is concentration. Concentration, again, is moles per liter. So, now we have our molarity. What if we added, and this is molarity for each, so, well, this is Ag plus is going to be 1.3 times 10 to the negative 5 moles, and then same thing for Cl, whatnot. What if we added 0.1 moles of NaCl? How would that affect the molarity of Ag and Cl and Cl? Obviously, this has Cl within it. We don't care about the Na because we're only looking for Cl and Ag, for silver and chlorine. So what happens? Well, we can input this into our math via the common ion effect. Roll credits. What we do is that, well, using this basic idea that moles is just the count of something, right? So if we have 1 mole, oh my goodness, sorry. If you had 1 mole of NaCl, that's essentially saying that once we break this up, we have 1 mole of Na and 1 mole of Cl. Except now it's 0.1 mole. So what we can do is that we can actually insert this into our Ksp. And instead of saying x times x, we'd say x, which is our silver, times 0.1. And this 0.1 is coming from the Cl that we have, is equal to our original K value, which is 1.6 times 10 to the negative 10. Cool. When we do this math, we find that, well, x is equal to 1.6 times 10 to the negative 10 over 0.1. And this just simplifies to 1.6 times 10 to the negative 9. So very clearly we can see that this silver value, this molarity for silver, is very, very different from what we had originally. In fact, it's much smaller. And this is just what happens when you add a little bit of like moles of Cl. And if we did this for chlorine, it would have the same effect because of the Chalet and whatnot. And that actually just wraps up the entire unit. That took quite a bit of time, but it was actually very, very simple in terms of like looking at stuff. I didn't get a chance to do this ice table, but at this point, I'm thinking that I can do this in the next part. Hopefully this was good for you, and bye.